So let's take a look here and let's look at the concentration of different parts of an acid when that acid ionizes. So let's just do a quick review. We know that a monoprotic acid is an acid with one ionizable hydrogen. And we know that a polyprotic acid has more than one ionizable hydrogen. Oop, And of these polyprotic acids, we have diprotic, which have two hydrogens, and we have triprotic, which have three hydrogens. Okay, so we know that our hydrogens are going to ionize, okay, when placed in water. Now these hydrogens will ionize stepwise, meaning one at a time. So let's look at an example. Let's look at carbonic acid. Carbonic acid is a weak acid, so when placed in water, it will lose one hydrogen to form a hydronium ion and HCO3 minus. Now this is in equilibrium because it is a weak acid. However, this HCO3 minus can also ionize. So this HCO3 minus in water will also form a hydronium ion and our carbonate as well. Now, the amount of ionization that is going to occur will be determined by the Ka value. So if you look at your reference table, the Ka value of carbonic acid, and we're going to call that the Ka1 because this is the first hydrogen to be ionized, is 4.3 times 10 to the negative 7. Now, this HCO3 minus can also ionize. So if you'll look at your reference tables, we're going to call this the Ka2 because it is the second hydrogen to be ionized. That value is 4.8 times 10 to the minus 11. So we will notice that there will be more ionization of the H2CO3, the carbonic acid, than the HCO3 minus because the Ka1 is much greater than that of the Ka2. So when we have a solution, and if we were to zoom into our solution at the particle level, what we would find is we would find that we do still have some carbonic acid, H2CO3. We have some hydronium ions. We do have some HCO3 minus because again, this is in equilibrium. And we also have some carbonate. Now, how much of each of these do we have? And if we were to look at it in terms of relative concentration, because our carbonic acid is a weak acid, we will find mostly carbonic acid in our solution. So since we have a large amount of carbonic acid, we show that with multiple greater than signs. The hydronium ion is going to equal our HCO3 minus, which now this is also the second Ka is also a weak acid in equilibrium. It is an even weaker acid, so we will get even less carbonate in the end. So our carbonate is going to be the smallest amount in the solution. So how do I know that these two are equal? Okay, so we have a small amount, but they are equal. And we have a very small amount of carbonate because of our Ka value of 4.8 times 10 to the minus 11. Okay, so let's look here. How do I know that these are equal? So if we were to take our equations that we've written, okay, so let's look at our equations here, and let's start with the first one. Our carbonic acid plus water is going to yield our hydronium ions, HCO3 minus, when we do our ice chart. So when we do our ice chart, we have our initial concentration of whatever the carbonic acid is. We have no products to begin with, but we add X. So at equilibrium, we have X for each of our two products. Now, this HCO3 minus will then ionize in water, again to form H3O plus and carbonate. So when we look at our initial for these, we have an initial amount of hydronium ions, and we have an initial amount of our HCO3 minus. They are the same because the equilibrium becomes the new initial, so the concentrations of each of these are the same. They are equal. And because this is such a weak acid and we produce so very little carbonate, the amount of change to change this H3O plus is negligible.